In this video we give another example of linear combination, but this time we will be using matrices. So we are asked to write the matrix E 3 1 1 minus 1 as a linear combination of matrices A, B and C, where A is 1 1 1 0, B is 0 0 1 1 and C is 0 2 0 minus 1. So what we have to do is to write matrix E as a linear combination, so that will be x times A plus y times B plus z times C, where x, y and z will be scalars from the field. Okay, so matrix E will be equal to x times A, y times B and z times C. So that's 3 1 1 minus 1, and then you just multiply the scalar by each entry in the matrix. So now have x plus 0 will be 3, so this one is done. Then x plus 2z will be 1. But x is 3, right? So 3 plus 2z is 1. So 2z is 1 minus 3. So 2z is minus 2. So z will be minus 1. So now that we have x equal 3, z equal minus 1, you just keep doing calculations and you will find that y is minus 2. Okay, so we can write matrix E as a linear combination. So x, this one will be 3, y will be minus 2 and z will be minus 1, right? So E is a linear combination of 3a minus 2b minus c. Now we will do some exercises on the linear span. If W is a subspace of V, that means that the span of W will be W. So let us say we have a vector space V and we have here W as a subspace. So the span of W will be W. And why is that? Because W is a subspace of V. So, and V is a vector space. So W will be closed under linear combination. And since W is closed under linear combinations, the span, if I pick the vectors here, the span of W will be a subset of W. But on the other hand, W is also in the span of W. So we can say that the span of W is W itself. Well, the conditions are W being a subspace of the vector space V. And now that we know this, we can also check that the span of of W, the span of the span. I'm calling this W. Let me change this for S now. So the span of S is the span of S. And this is easy to see because the span of S, this will be obviously a subspace of V, right? So the span of S, this span here, the span of S will be a subspace of V. But now, using this, since the span of W is W itself, we can say that the span of the span of S, it's like the span of S. Now let us say we have S and T, and they are both subsets of a vector space V. But let us say that S is a subset of T. We are going to see that the span of S, since S is a subset of T, the span of S will be a subset of the span of T. The proof is really easy. So let us pick a vector V that belongs to the span, I call it S, right? Let us pick a vector V in the span of S. So if V is in the span of S, I can write V as a linear combination U1 A1 times U1 plus A2 times U2, etc., plus AR times UR, where these scalars are from the field, and these vectors UI are from the set S. Okay, so V is from the span of S, so I can write V as a linear combination of scalars and vectors in S, right? But we cannot forget that S is a subset of T. So, since S is a subset of T, we can say that all these vectors, UR, U1, U2, etc., so UI, they will all be in T, okay, because S is a subset of T, so we can say that all vectors U are in T. So if all vectors U are in T, we can say that this vector that we picked, vector V, is also in the span of T, right? Because we wrote V as a linear combination of vector U. So since V is in the span of T, an arbitrary vector, we can say that the span of S is a subset of the span of T. And that concludes the proof.